Hey guys, happy snow day. I'm making this on our snow day. So hopefully you're doing something fun today. Well, I guess you're watching this a couple days later, but hopefully you had a good snow day. You follow, right? Okay, so I have a two-part video. We're gonna start with this first part, but both videos together are gonna be about this idea called QSP and then what I call the monster problem, a big, long, scary-looking problem, but if we break it down into steps, it's not so bad. So in this video, I'm gonna focus on the QSP part, and then in a later video, you can watch me work through a monster problem. All right, we saw Q versus K last unit in equilibrium, but now we're going to look at something called QSP. And what QSP is it's used to determine how saturated a solution is and if a precipitate will form. Well, that sounds kind of complicated. Why can't we just relate that to what we've been doing? So here we go, I will. If I say we are going to use it to determine how saturated a solution is, remember, if it is saturated, we are at equilibrium. So really, I'm asking, are we at equilibrium? We know from equilibrium unit that if Q is equal to K, we are at equilibrium. If Q is not equal to K, then we are not at equilibrium, and we're going to shift one way or the other to get back to our equilibrium position, our K. And then the follow-up question, if a precipitate will form. Well, when you think about these reactions, it's a solid breaking into the ions. So really, when I say will a precipitate form, I'm specifically asking, will the reaction shift left? Meaning, is Q bigger than K? Because when Q is larger than K, we shift to the left. And the left side of our reaction is the solid, that's the precipitate. So once we know K, we can say if a precipitate will form, will it shift left or not? And the monster problem, which in our next video, you'll see what are the concentrations of ions required to get this, to get something to precipitate. All right, so similar to last unit, we can solve for QSP at a specific point in time. So I wrote this generic reaction, the solid breaks apart into A plus and X minus. KSP would be these guys at equilibrium. So I'm putting my little EQs. So that means QSP would be the same thing, but just at a different point in time, or we're not sure maybe if we are at equilibrium. So what I can do is I can compare QSP to KSP. So if Q is less than K, what this means is we are going to shift right, which is towards the products. So on this reaction, we would move to the right. And what that does is it would increase the concentration of the ions and decrease the concentration of the solid. Essentially, more solid is breaking off into the ions. So we would say it's still considering, like we're still in the dissolving phase. So our solution at Q is unsaturated. We are gonna move to the right. No precipitate will form. We're still dissolving that solid. If Q is equal to K, that means we are at equilibrium and it is perfectly saturated. So no more could possibly dissolve, but that is our equilibrium for these reactions. Then, if our system is not at equilibrium because Q is larger than K, we're going to shift left. Which is towards the reactants. You should say just reactant. So if we're shifting this way, that's when Q is larger than K. And what that will do is we are going to use up some of the ions to form more solid. So the ion concentration would go down and we're making more solid. Because we are making more solid, that means we are forming a precipitate. So a precipitate will form when a solution is oversaturated, meaning there's too much of the ions. Q is larger than K, right? So if these are bigger than my K, then we're going to shift to the left to get to K, and a precipitate will form. In our lab that will do next week, I'm going to give you something that is already oversaturated. You should be able to even see some of the solid in there. And what we can do is if we filter out that solid, we can then have the aqueous part that's left over once the solid is removed will be perfectly at equilibrium where Q and K are going to be equal. So that's something we'll see in the lab. I give you something where Q is larger than K. We'll filter out the solid so then it is perfectly at equilibrium. One other thing to note is a lot of times these questions won't look like a Le Chatelier or a Q versus K problem. They will give you maybe the KSP value and then give you a way to find the molarities of A plus 1 and X minus 1. And then they'll just ask, will a precipitate form? And really what they're asking is, will this reaction shift to the left, right? Because if I'm saying, will a precipitate form, I'm asking if, so sorry if I cut off there, but really what I'm saying is if a precipitate forms, I'm asking, is Q larger than K, meaning will we shift to the left? All right, so here's how we solve for QSP. Usually they're going to give you the concentration of each ion and then a new total volume. So we're mixing these two things, will a precipitate form. So we're going to have to do M1, V1 calculations for each of the ions that make up the solid. And then once I know those new M2, those new molarities for each ion, I'm going to substitute those into the QSP expression, which remember is the same as the KSP expression. And then I will be able to compare Q to K. K will be provided, and I can see if Q is larger than K, then we will shift towards the solid side and a precipitate will form. So let's actually try one of these problems here. It says that we have 750 mils of Ce3 plus, and they give me the concentration, added to 300 mils of a certain concentration of IO3 minus. Oops, there we go. And they want me to say if the CeIO3, which they've provided the KSP, will precipitate. So first, I'm going to write this reaction. Sometimes they give me spectator ions. Notice here they just told me the cation and the anion. Sometimes they will give me spectator, so it's helpful to write your main KSP reaction so you don't get confused about what's important. So there's my KSP, my KSP reaction where the solid breaks into the ions. And so now what we need to do is that first step, and we need to find the new concentration of each ion. So here is my first one. We want to find Ce3+. And I started with a concentration of 4 times 10 to the negative third molar and 750 milliliters. It is not going to remain that concentration because, so we're going to look for M2, because I'm adding to it a separate solution. So really my new total volume is going to be 750 milliliters plus the 300 milliliters from the other solution. So I can do some math and I get a concentration or an M2 value of this Ce3 plus ion as 2.86 times 10 to the negative second molar. Now let's do the same thing with my IO3 minus. I started with a molarity of 2.0 times 10 to the negative second molar, and that one was just 300 milliliters. I want to find the new concentration of this ion, and my grand total is going to be 750 from the first thing plus the 300 that this guy was a part of. So when I do my math, I get a new concentration of IO3 minus as 5.71 times 10 to the negative third molar. Perfect. So now let's look at my balanced equation. And I'm going to write my QSP expression. So at a certain point in time, not necessarily equilibrium, QSP is going to be my product times my other product. Don't forget this guy is cubed. So I can plug in any point in time. Well, perfect. I have this guy and I have this guy that we can plug in. So QSP will be equal to 2.86 times 10 to the negative second 5.71 times 10 to the negative third, and that guy is cubed. I would use parentheses on your calculator to make sure that we're just cubing this guy and not the entire thing cubed, just this one is cubed. And so when I math that out, I get my QSP is equal to 5.34 times 10 to the negative 10th. What we're going to do is compare that to the provided KSP, which they told us up in the problem right here. So if I can compare KSP is equal to 1.9 times 10 to the negative 10th. Let's compare these. I can put them on a number line. I see, well, they're both times 10 to the negative 10th. So really, all I'm doing is comparing 1.9 to 5.3. This is Q, this is K. So which way are we going to shift? Well, Q is always trying to get to K. So because QSP is larger than KSP, reaction shifts left. And because my reaction is shifting to the left, that means a precipitate will form. So basically what we've done when we've mixed these two ions, we've created an oversaturated solution which will force a precipitate to form. Here's that same thing just written out. I wasn't sure if I was going to talk through it quickly or go through it, so you can look this over if you need to. Okay, will AgIO3 precipitate? So that is my solid. If I'm asking for that to precipitate, this one is my solid. And you can confirm that because that's what they gave me the KSP for. When 100 mils of 0.01 molar AgNO3 is mixed with 10 mils of 0.015 molar NaIO3. So in this case, they're giving me some extra stuff. What do I care about? Well, in my first solution, 100 mils of 0.01 molar AgNO3, all I care about is the Ag+. So in this case, if I have 0.01 molar AgNO3, that is the same as 0.01 molar Ag+. Why? Because it's a 1-to-1 stoich. What about this guy? If I have 0.015 molar NaIO3, well, I just care about the IO3, so Ag is coming from the green, IO3 is coming from the yellow. Well, this one is also a 1-to-1 stoich, so that means I have 0.015 molar Na+. So these are going to be your M1s for your M1V1, and so I would like you to pause the video and try to find your M2 for Ag and your M2 for Na+, or excuse me, let's just rewind really quick. Ms. Buller, I need you guys in class to correct me. We don't care about Na. We just care about this IO3 minus because it's the yellow one. Luckily, it's also 1-to-1. So anyways, okay, so here's your M1 for Ag+, IO3 minus. I would like you to do M1, V1 for each of those and find the new M2 values to plug into your QSP. So pause the video. I'll put the answer up in 3, 2, 1. All right, so hopefully you did your M1, V1s, got your new total volume, got a new concentration of Ag. Same thing here, using the information for IO3, new concentration of IO3. QSP is my products divided by my sneaky solid reactant, so we don't care about that. We plug in this value and this value into my QSP expression. And what we'll do then is we will compare QSP to KSP. In this case, Q is bigger, times 10 to the negative 5th is larger than times 10 to the negative 8th. So in this case, a precipitate will form. The reaction is going to shift to the left. All right, so hopefully you realize that QSP problems are not that bad. In the next video, I'm going to talk about the monster problem. Rawr! Monsters. Monster meaning it's just a really big, long problem. So what we just learned is actually step 1 of the monster problem. Find Q, compare it to K, see if a precipitate will form. Then what makes the monster problem a monster problem is when you say that the precipitate will form, they will also ask for how much precipitate will form. So I'll show you those steps in the next video. I hope this one was helpful. I'll see you in class.